lesson two. So just an introduction to related rates. And the first thing you want to do, what we want to do, so there's several different ways to find the entryway to this. What we're used to doing is, for instance, we're looking at the circumference of a circle. It's just 2 pi r. What we're used to doing is saying dc over dr, like this derivative would actually be just 2 pi. But what we're going to have to do is do this with respect to time, right? So if c equals 2 pi r, and we're doing this with respect to time, we're going to do this to both sides. So we're going to do this with respect to time, and it just becomes 2 pi dr dt. And how might we look at this? So this original equation, we could look at it as a function of time. It's a function of time. And typically, most functions that we're going to encounter, they are functions of time. So let's look at the area of a rectangle. So the area as a function of time would be L sub t times W sub t. And I just realized that these are functions themselves, right? Now, with respect to time, oh, I should have put sub t right here. It'll be d sub a over d sub t equals, and we're going to use the quotient rule, so f of x equals L sub t, right? And f prime sub x equals, we're going to use the product rule, dl of dt. Similarly, our g sub x here is w sub t, g prime sub x is dw dt. Now, product rule says w dl dt plus l dw dt. Perimeter of a rectangle, perimeter, it would be 2l plus 2w. I'm going to get the derivative here, so dp with respect to time, dp equals 2 dl dt plus 2 dw dt. Area of circle, area equals pi r squared as a function of time. That's an r, and it's squared, r sub t, and it's squared. Now, as a derivative, we just really simply write the derivative of a over dt equals 2 pi r dr dt. Area of a square. Okay, and this is a function of time. Derivative would be dA dt equals 2s ds dt. Volume of a cube, s cubed. As a function of time, this derivative would be dv dt, 3s squared ds dt. All right, so moving on, the volume of a sphere, volume equals 4/3 pi r cubed. As a derivative, it will be dv dt equals 4/3 times 3 pi r squared dr dt. Simplified, that would just be 4 pi r squared dr dt. Volume of the cylinder would be volume equals, let's see, pi r squared h. Now, we can do the product rule here, and we would get dv dt. And this would be f of x here, this would be g of x. Okay, so we have f prime, which would be 2 pi r h dr dt plus c pi r squared b h dt. Okay, volume of a cone 1/3 pi r cubed, just simply be dv dt. Making sure I did this right. Volume of a cone pi r cubed, nope, pi r squared h. And let's make sure that is correct. So remember, when I don't know something, I'm going to go Google volume of a cone. And of course, it's going to take forever. Volume of a cone. Oh yeah, the servers are down. There's that. So I think it's 1/3 pi r cubed times or squared. If it's squared, then there's h involved, and I do believe there's h involved. So volume of a cone. And of course I'm on my phone. Oh, and I'm right. So that's a squared. And we have a product rule going on there. So here's f of x, and here is g of x. So first, um, f prime of x, which is 2r, 2/3, 2 pi over 3, r h dr dt plus 1/3 pi r squared dh dt. And this is just all with respect to time. That's where it's going. So we're used to seeing it a different way, but that's with respect to time. So the area of a triangle is 1/2 the base times the height. Um, so if I wanted to write this derivative, dA dt equals 1/2 h dB dt plus 1/2 b dh dt. And I use the product rule on that. Let's see if there's anything else. Okay, so we're going to do some translations here. And here we have the depth or the height is 2 inches. So the depth of the water rectangular pool is decreasing at a rate of 2 inches per hour. So decreasing. So dH dt equals -2 inches per hour. Here's my units. 85 vehicles. Okay. And here, vehicles per hour. So dVEH dt would be 85 vehicles per hour. A spherical balloon contains 15 cubic meters of air, so V equals 15 meters cubed. Air is escaping, so dV dt equals -15 meters cubed. The area of a square is 24 meters squared. The area, so dA dt, is decreasing at 24 meters per minute. So interpretations of derivatives, things you want to look for specifically is something that's happening at a specific instant. So when t equals 24 or at the end of 24. So basically this function g, so the temperature in degrees at a specific hour. So 24 per hour, 24th hour. So a change in temperature during the first day, doesn't work. Changing temperature during 24th hour is questionable because they're talking about change, but I need to see some keywords here. Rate and maybe at 24, or when t equals 24 hours. Like stuff like that is what I want. So the rate of change, so the rate of the temperature per hour, things like that. So the average rate, definitely don't care to see. The rate at which the temperature is changing during the first day, the during, I need it to be at, during. So the temperature rate, which the temperature is changing at the end of the 24th hour, is perfect. Now we're going to look at linear approximation. So this is basically where you're looking at a curve. So if I have this curve, right, what it does is, let's say that this is, let's get a different color here. Okay, let's say that this is a tangent line coming off this curve. I want to guesstimate what, let's say that this is 2.3, x equals 2.3 right here. I want to guesstimate what this y value is, right? What they do is they make you get the equation of this tangent line, and instead of being able to get the point right here, specifically right here, you get the point, the y value of this tangent line, this y value here. And this y value is only approximately close to whatever the y value is right here. So if this was 2 and it was 3 right here, then this y value would be an underestimate of the y value of the actual y value. This is my actual y value. Actual. And what you'll be calculating is this approximate y value using the equation of the line tangent at a point close to it. So here, typically when it's concave up, because the tangent line falls below, you're usually coming up with underestimates. Here, because it's concave down, you're usually coming with overestimates. Okay? So this is what is the best estimate for f of 3.8 using local linear approximation for f at x equals 4. So first, they tell me what this point of tangency is. It's 4, 5. They tell me the slope. I can write an equation. It's y minus 5 equals 3 times x minus 4. Now I want to approximate. I want to approximate a point, a y value for a specific point. I want to get a y value for this point at 3.8. So I'm going to replace this first x value in this tangent line equation. And I have y minus 5 equals 3 times 3.8 minus 4. I get 3 times negative 0.2. Y minus 5. So y is approximately negative 0.6 plus 5, or 4.4. So is this a underestimate or overestimate? This is a underestimate. So y approximately 4.4 is an underestimate because f is concave up. And that's the appropriate way to answer that question. Number next works the same way. We have the function 5x minus 2x. Minus 2 is concave down at x equals 1, so f of 1, so my point of tangency right here, POT, is 5 times, I think this is squared, times 1 minus 2 times 1 minus 2, and that's squared. And I get 5 minus 2 minus 2. And I get 1, so my point of tangency is 1, comma 1. My equation here is y minus 1 equals x minus 1. I need my slope, so I'm going to say f prime of x equals 5 minus 4x, okay? So f prime of 1, this is my slope, is 5 minus 4 equals 1. So 1. So I want to estimate this value, so I'm going to replace this x, and it's just repeating the process. And I find myself saying y minus 1 equals 1 times 1.1 minus 1. This is 0.1. Y equals 0.1 plus 1, or 1. So y, when y is approximately 1.1, the estimate for f of 1.1 is an overestimate, because f is concave down at x equals 1. And that's all you do for linear approximations, is write the equation of tangent line of f at the point 2, 0. So I'm going to let you do that for some homework practice there. And we're going to move on and end it right there. Let me see if I can get that problem now. Oh, there it is. Ooh, okay. So sorry about that. I actually do want to do this. Okay, let me do it right here. So dy dx equals e. Let me see if I can get the actual problem there. It's not coming up correctly. But yeah, so on this particular problem, just kind of going back, this is your slope here, okay? You can find an equation, you can say y, this is your point of tangency, to 0. So you'll get your slope from dy dx, so it'll be like saying 2y minus 0 equals dy, whatever dy dx is, times x minus 2. And you can get that slope easily. You'll have your tangent line equation. When you go to approximate values, this 2.2, you'll be plugging it in. All right, so nothing hard about that. Have a good day, guys. Take care.